Okay, we're recording. Hopefully everyone can hear me. I think the transcript kind of implies that it's working, so that's good. Yeah, I'll keep an eye out for questions as usual. But yeah, this is still a hybrid workshop. So yeah, I'm in the main library. Sorry, I'm in the law library. You can see my message earlier in the chat if you're still trying to make your way in person. But yeah, so today's the last shoot. We've reached towards the end of this subject. Here you can see that our lesson plan for today isn't as packed. Like, it's still a little bit packed, but it's not as packed as last lesson, which again, yeah, I thought was the hardest topic. So yeah, we'll be starting off with talking about Newton's second law. So picking up pretty much where I left off. So for those of you who weren't able to stick around for the last 10-ish minutes of last workshop, I tried to dive into Newton's second law, at least talking about mass moment of inertia, that part. So I'll do a brief recap just at the start of this lesson for that. But then we'll be moving on to our work energy methods and our impulse momentum methods as well. And that's pretty much all of rigid body kinetics. I guess if you recall earlier in dynamics for particles, we had a separate lesson for work energy, and we had a separate lesson for impulse momentum. But the good news is, even though there's a lot packed into this lesson, it's almost the exact same as for particles. That's the good thing. It's just everything's just changed slightly. Like, the methods aren't completely new, like in rigid body kinematics. Okay, so without further ado, let's talk about mass moment of inertia. So this is pretty much what I was talking about towards the end of last lesson. Just pulling up my notes, give me a second. This is from the end of last lesson, and I'll just briefly recap on it again for those who missed it. So mass moment inertia, where it plugs into things is pretty much when you're looking at Newton's second law. So for rigid bodies, you can look at the translation. And those are some of the forces equations that you can use. But there's one more for rigid bodies, which there isn't for particles, right? And it looks like that. And that's saying the sum of the moments is equal to the mass moment of inertia. That's that. About 0.0. So yeah, this is for a body that's rotating about 0.0, right? And that's the angular acceleration alpha, right? Yeah, the units are kilogram meters per second. Oh, sorry, kilogram meters squared, right? And yeah, so let's draw out something. So like the example I had from last lesson was you have this pin support. I don't know what button brings up that menu. And then you have this rod that's dangling off of it, for example, and then there's a disc attached to the end of that rod. So that's like a composite shape because we have these two shapes. G denotes the center of gravity for an object, right? And the overall shape will have some sort of center of gravity over here, and you can work that out using the center of mass kind of working, right? So pretty much, if we call that 0.0 and we just talked about G, then let's not talk about the composite object for a second. Let's just talk about this rod. So pretty much the mass moment of inertia is about 0.0 is the mass moment of inertia about its center plus the shift distance, right? So this is called parallel axis theorem. I didn't drop this this term last workshop. But it's saying that, actually, first of all, I should mention, the mass moment inertia in short terms is pretty much a measure of the resistance to rotation, right? It's a measure of resistance to rotation. And if we shift it so that an object's further away, if its center of gravity is further away from where you're rotating it from, it actually increases in this rotational resistance, right? So that's what this this component is factoring in, right? It has a shift distance and yeah, that formula, right? Okay, and then basically the mass moment of inertia for certain shapes, right, is different, right? And the common ones I've highlighted in blue here. So you'll be dealing with rods, you'll be dealing with like discs, and there's one question of a hoop as well, so you got to look out for that. You'll come to learn the difference between the rod about its center and the rod about its end, but essentially they're the same thing, but with the shift distance included, right? For the case of the rod about the end. So yeah, it'll make more sense when you see a question, pretty much, right? So just continue my explanation on mass moment of inertia. So for rigid bodies, we talked about these equations. Newton's second law. Right? So there's where the mass moment of inertia sits, right? Okay, so if you imagine we have a particle, let's say a box, that's being pulled with a force of F, right? And we keep that force consistent, but we decrease its mass. It's going to accelerate more, right, with the same amount of force. And conversely, if we increase its mass, it's going to accelerate less, right, with the same force. So when we're looking at mass moment of inertia, there's a similar concept. Keep in mind that's big M, so that's moment. Right. So if we apply some moment to a box that's hinged like that, that is attached to a pinned reaction, rather, pinned support, yeah. And then we apply some external moment to it. If it has a higher I, it's going to have like a higher resistance to rotation and therefore a lower angular acceleration, right? And same thing, if we have a low I, it has a low resistance to rotation and therefore it's going to accelerate a lot, right? Have a lot of angular acceleration, right? So that's kind of how you got to think of I, essentially, right? It's to do with the shape as well as the mass of each individual component. So if we're talking about this, we're talking about say that's 8 kilos, it's like 12 kilos. Depends on the mass as well of each of these objects. So I'm going to check the chat for questions. Okay. Do you guys have questions as well? Or? Okay. Yeah, all good. So yeah. Okay, so moving on. Oh, I want to highlight one more thing quickly, and that's that I, right? If you look up moment of inertia, right, on Google, you're going to get two different versions, okay? So I've been very careful in calling this the mass moment of inertia, because that's the one we use in this context. But there's also area moment of inertia. I think that's what it's called. So that's different. Pretty much, in short, it's useful for if we have like the cross section of a beam, for example. Actually, in the civil version of this course, run in term 2, they have a week just dedicated to finding area moment of inertia. So it's like a geometric property of the shape, and it tells you how much that this shape will bend in like the x-axis or the y-axis. But if you're doing mechanics of solids, maybe like next term or in one of the terms this year, you'll find out about this very soon because it's the first week of content for that course, pretty much, right? So basically what I'm trying to say is you'll stitch yourself up if you use the area moment of inertia formulas for certain shapes rather than the mass moment of inertia ones while doing these questions. So you want to stick to the mass moment, right? Okay. So let's continue talking about Newton's second law a bit more. Because here I've written the sum of the forces in the x direction, sum of the forces in the y direction. However, we know that we can take the sum of the forces not only in those directions, but like in the normal and tangential directions for objects, right? So when you're analyzing your questions, you have to think about which directions are tangential. That's tangential to the motion, right? To v, or like how the linear velocity will be moving for the object, and normal acceleration. Okay. So here are the formulas again. I think I made a mistake, to be honest. In question 3 last workshop, where I swapped around these equations, so AN and AT. Yeah, I've corrected it in my notes when you look back at it now, but in that recording, it's wrong. So sorry about that. So yeah, just recapping. That's what we talked about last lesson, right? And not only last lesson, I think this might have come up in particle curvilinear motion or something. But anyway, so if you haven't seen those before, we'll be using those for Newton's second law for rigid bodies, right? Okay, so let's look at this example, right? So what I have is I've got your pinned reaction, pinned support that we called O, and then we have a rod dangling off of it, and we're applying this force P at the end of the rod, right? So you want to be thinking about which way is this going to be moving due to this force, right? And therefore, which way is our tangential acceleration and which way is our normal acceleration going, okay? So if you had to look at this, you can probably deduce that it's going to move that way, right? In terms of like linear velocity, say at this point. And yeah, basically our AX, right? So our, for rigid bodies, you want to be thinking about everything relative to kind of the center of mass, right? So which way is this accelerating pretty much? So is that the tangential? Is AX the tangential or the normal component, right? So that's going to be tangential, and that's tangential to the direction of linear velocity, right? And then the normal direction is going to be centripetal, which is like towards the circle, right? So that's the circle. That's the path of G, or whatever, right? It's going in towards the circle, right? Anyway, that's a long way of just saying that that's equivalent to AT, that's equivalent to AN, right? Okay, let's look at these forces, and I'm going to erase this quickly to clear up some space. So at point O, there's actually reactions happening at this pin, right, which is going to be relevant for this topic. You can also call this ON, OT. You can call this OY, or you can call this ON. So O standing for the point O. So if this is point A, you'd call this like AYAN, right? Alright, so let's look at the forces in the x direction, right? Taking right as positive. We have this force, which is P, right? And we also have this reaction force, right? So that makes sense. We've just been doing what we've been doing before, which is just having, I like to keep all the forces from the free body diagram on the left-hand side of that equation. And for AT, well, it'll just be equal to alpha R, right? And what is R, right? So R is pretty much from O to G, right? It's kind of like, so if we're talking about the path, the path which this object would swing, R is the radius, right, of that path. Yep. Okay, and then let's look at the sum of the forces in the y direction. So we've got OY, right? But we've also got MG, right? So we can't forget about our weight force. Because this is elevation view, we're looking at this object, like the up-down direction is vertical, right? So the acceleration due to gravity is going to be relevant. Okay. Let's look at the formula quickly. Actually, I'll just write it out. So the normal acceleration is angular velocity squared times r, right? We talked about what r is, but let's think about angular velocity. So in this instance of time, we're told that it's going from rest, right? And we know that angular acceleration, angular velocity, is v on r, but since it's at rest, is 0, right? So this whole right-hand side is going to be equal to 0. But yeah, anyway, let's look at the sum of the moments, because this is new. Well, sum of the moments isn't new, but what we're going to do with this equation is new. Okay, so looking at the forces, if we're taking the moments about O, right, if you remember from statics, we have to look at P, which is, so like mg has the same line of action, right, as O, so we don't need to look at mg, but we have to look at P, because that one has a line of action that's perpendicular, and we have to look at the lever arm as well, right? And the lever arm, let's call it D. Specifically in this example, I chose D and R because, yeah, if this is a rod, if it's just like a normal rod or whatever, D is 2R, right? It's just 2 times the radius, but let's just call it D. Okay. For IO, right, you can calculate it in 2 ways. Okay, so the first way is considering it as a rod about the end, right? Because we're rotating from this point, right, which is the end of the rod. So we can use that formula. That formula looks like this from the little diagram I included from the previous page. Or you can look at it as the rod about its center, plus parallel axis theorem in terms of shifting, right? So that looks like this. Right? So D being the shift distance. So actually I've kind of doubled up on my letters here. I've called this D, but the shift distance is how far you have to shift it from the center of gravity to the point of rotation. So that's actually R, to be honest. The general formula goes calls that D, but in the diagram that I've drawn just now, that's actually R, right? That's the distance that you shift it, right? So you can use either of these formulas, it's fine. Do you have questions? Or let me check online as well. I'll answer that in the break about the note-taking app. I've actually got that question before in one of the earlier workshops. I think it was like an in-person question. Okay. Yeah, so basically, I've told you a lot of theory, but we haven't looked at any particular questions, right? But this is like the thought process you go through these questions in. Another thing to note is that if you have all these numbers, right, P, D, and you worked out I, right, based on the shape and weight of the object, you've actually got to use this equation, the sum of the moments one, to find angular acceleration first, right? Because if you take the sum of x, right, what you won't know is you won't know the support reactions. You're usually solving for those, right? And you also won't know alpha, right? So you have to go from this one to this one, right? Because then you plug in alpha. That's generally the steps that you take. Let's look at it in action, all right? So this one's a slightly more complicated example than what I just talked about, but it'll be good to run through. Okay, so let's read through the question. So we have two rods. So this is a composite shape because they're attached to each other, right? But they both have a mass of 8 kilograms, right? And they're both 0.5 meters long, right? I won't highlight that. The bars have an angular velocity of 4 radians per second as OA passes through the horizontal. So this is the snapshot in time that they've drawn on the right. It wants us to find the total force R at the support, right? So say you have OX, OY, whatever. O is this, right? Remember? Oh, sorry, not O. I called it R, right? So we're just finding the magnitude of both components of the pin support, right? Before I draw the arrows on, so that's just what we did in if you remember in statics, right? We always drew the arrows facing in these directions, right? It's like A, X. Oh, you don't have to, but this is the way that I did it, and there's no consequence of doing it like that, right? But in this topic, we have to be a bit more mindful of which directions we set our support reactions in, because you'll end up with the right magnitude, but yeah, you just have to use your logic to figure out the actual direction of the vectors. I'll tell you what I mean by that. Okay, so say this is going clockwise, okay? Right, so just based on the wording and this bar, we assume that it was up here and then it fell to this position, and yeah, it's going clockwise pretty much, right? See where I go next. Yeah, the first step is always to find IO, right? If you're not given IO immediately, you just pre-bake this step every time. So that's kind of why I included it at the end of last workshop, because it's useful, right? So I'm going to use the rod about its end formula. Right, for IO. So we're calculating the individual components first, right? M was 8. The length of that rod is 0.5, right? That's just 2/3. Okay, so for BC, right, I'm going to take rod about its center, right? Rod about its center here. And I'll explain the logic behind this. So rod about its center and parallel axis theorem shifting, right? This one was also the same mass and the same length. But let's look at D, right? So here's this object. Center of gravity be over here, right? And the center of gravity for this object to be here, right? So for rod BC, what would the shift distance be? Would it be 0.25? Would it be 0.5? Okay, so here's the direction of shift distance. Right. So for a rod about the center, right, we've shifted it that way. And in this course, I think, yeah, I'm 100% sure, you'll only be given symmetrical shapes, right? Do you see how this is a T shape? And before I was talking about a pendulum or something that looks like that. Parallel axis theory works in this direction, right, for shifting. Imagine if you were given a shape that looked like this. Then you have to use something called perpendicular axis theorem, right? So this is the perpendicular axis, right? That's not in the scope of this course, so don't worry about that. So anyway, yeah, that's why the shift distance is that way. Okay, so therefore we're going to shift it 0.5, right? And when we plug in all those numbers, we get 2.167. And in order to get IO every single time for a composite object, you just sum it, right? You sum all the individual components. Because each individual component, if you think about it, is going to increase the resistance to rotation, right? Similarly to if you have like one tennis ball or something, right? And then the composite shape of two tennis balls is you just add the masses together. It's very similar, but for rotational resistance, which is IO, right? Yeah, so that's that. Okay, so now we're moving on to the stage of Newton's second law. And like I mentioned earlier, the first step is going to be find alpha. Alpha being the angular acceleration, right, which is going to then plug into our tangential acceleration. So let's look at this again. So I'm going to draw the support reactions, and okay, here's the way I like to think of it, right? Here's the path that our object's rotating, right? And we can think of it like going clockwise, right? That's the direction of the motion, v, right? And so therefore, our tangential component of acceleration is going in the same direction, right? However, the reaction in response to this is going to go the other way, right? So you set it that way. Let's call that which is tangential, right? Okay, for the normal component is centripetal, right? So it wants to go in like that. And for this case, your reaction is going in as well, okay? And I'll tell you why. It's going the same way as the normal component because if you think about this path, right, and then this is swinging, it's the weight, forces, and all that of this object is going to want to spin out of the circle. It's going to want to be centrifugal, right? So away from the middle of the circle. And so our reaction is going to want to pull it in, right? That's the way you want to think of it. So these are the correct directions for our support reactions. It doesn't really matter because the question is just asking for the magnitude of R, but I guess it's good to still get the directions correct for our support reactions. And how you draw it is going to make a difference because this is just something I noticed, but like, let's see. In these equations, right, like for example, omega squared, if you plug in a negative omega or a positive omega, you're gonna get the same number, right, because it's squared. And so you're not going to get the right directions if you don't set the directions correct for our support reactions, right? Yeah, hopefully that makes sense. You get the magnitudes right, but you get the directions. Like you get the same answer if you set it that way, right? For this. Yeah, that's what I'm trying to say. Okay, that doesn't really matter. Let's keep moving on. Okay, so there's a big tangent. We're going to do the sum of the moments first because of the reasons I mentioned earlier. You're going to end up with only one unknown which you can solve for, right? So let's look at this. We have center of gravity of both of these rods, right? That's causing, so like the weight force is what's causing the moment, right? And this is perpendicular to our rod, right? Like these forces are perpendicular to our rod. And so our lever arm is simply going to be 0.25 for that one and 0.5 for that one, right? So that's what I'm going to write out. Oh, firstly, let's figure out mg. It's 8 times 9.81, right? That's 78.48 newtons. And it's the same for both the rods because of the same length and the same mass, importantly, right? So, oh, sorry, done something wrong. Okay, so I've automatically just done the moments counterclockwise, but you want to do the sum of the forces and the sum of the moments in the directions of motion, right? So so do you remember how we're talking about this spinning clockwise? We have to have our sum of the moments going clockwise as well, right? And the reason for that is because our angular acceleration is going clockwise, right? So it's the same reason why for our particles, right? If we have a box moving that way, it's more optimal to do some of the forces going that way, right? Because you're going to end up with the AX component that's going that way, right? Same reason. So just do it in the direction of motion. Therefore, gravity is going to be a positive vector because it's causing a clockwise spin. The weight force, rather. And now we're just going to plug in this value for mass moment of inertia that we figured out. Right, and now the only unknown we have is alpha, right? And we can just solve for it. It's not bad. Just do this. And that's going clockwise, right? Okay. We can do the sum of the forces in the x or the y direction next. Similarly for beams, right? Where it didn't really matter if you did y or x most of the time, right? As long as you do the moments first, you can use either one. So I'm doing it in the direction of the normal acceleration, right, which is centripetal. Here I've written a subscript 1 plus 2 so that we don't forget about all of our mass for our composite object, right? And then OX, we pointed to the left, right? The support. Yeah, and that W was 4 radians. Yeah, the question doesn't even tell you if it's clockwise or counterclockwise. I just assumed it was clockwise. The reason is because if this is whichever one, if it's negative, it gets squared out, so it becomes a positive number anyway. Okay, so what's radius, right? Because before, we just had a rod that was like this, and radius was from the end to the middle, right? But now the radius, well, there you go. For anyone who was asking which program I use, it's Notewise. See there. The center of gravity for our composite object is going to be somewhere here, right? Intuitively, you can kind of just look at that and be like, yeah, sure, right? And the center of gravity is going to spin along that path, right? But we have to calculate that, right? Which we're going to call R. Okay, let's redraw it down here. So when I say G, I mean the center of gravity for the composite shape, right? The overall thing. Draw it up here. So yeah, it looks something like this, right? It's O. Call this G1 maybe. That's G. It's G2. And we want the radius from O to the composite center of gravity, right? This is 8 kilos. This is 8 kilos, right? This would be 0.25, 0.25, right? Okay. So we applied the if you remember this formula, right? In the x direction, it goes like this. Sum of the masses times the distance, let's call I, right? So what I means is each individual element. So we have 2 elements. So I could be 1, I could be 2, and you just sum them, right? So it looks something like this in practice. So this is for the center of mass. right? There's an 8. This whole thing's 16, right? 0.25, 0.5, right? We get that R is 0.375, right? That's the number that we're going to plug in for R. Right? And so we get our horizontal reaction. It's going to the left. Right? Moving on, we can do some of the forces in the y direction downwards. Downwards because that's the direction that the center of gravity wants to go, right? So 16, right? So 2 mg, right? Because little m is the mass of the rod, and that's the weight forces, minus Oy. So if you remember, Oy is pointing up, and so when you take the sum of the forces downwards, it's a minus. R was what we calculated, and alpha was what we found in the first step with the moments. So that's 20.774, right? When we rearrange for Oy, we get this. And that was pointing up, right? So now this last step's the easiest step, just Pythagoras. Plug in our numbers, and we got 101.29. So that's the answer. Not that bad, right? Compared to last lesson. Oh, my computer's really slow. Here we go. Is this our last workshop? Yes. Oh yeah, Jerry said that. Oh yeah, that's a revision one. I believe that's a lecture. I don't think I'm running it pretty much, so it should be at the lecture time, but I can confirm that for everyone. Okay. All good. So let's move on to this question. Okay. In terms of our lesson plan, I'll do this question, talk about work energy methods, and then we'll have a break, quizzes. I'll see which order is more appropriate depending on how we're feeling. But anyway, so here's question 1. So this is actually kind of a hard question, but it's the one that they've included in the workshop. Okay, the other ones that I've provided, they're not this bad. So that's actually why I've included that example from earlier, because that's like a nice stepping stone kind of to this one, because this one's actually pretty hard, right? Okay, so one thing this question says is that the frictional moment is 2 Newton meters. You'll see what that means, but it just opposes the direction of motion. It's very similar to rolling resistance in terms of forces, but yeah, very similar to rolling resistance, right? Frictional moment, but they just give you frictional moment. You don't have to calculate anything else, but you'll need it in one of the steps, right? They also just straight up give the IO, right? Which is also why I don't think it's a great question for demonstration as the first question. That's why I did the previous one first. Okay, so let's look at this question. Recall that AT is alpha R, right? So pretty much, in order to work out the net moment on the system, right? Because we have this disk that has like, I think there's a groove, they call it, this groove on it, right? And there's these weights attached to them by like some sort of rope, right? So we need to know which direction it wants to spin, pretty much, right? And not only that, we want to calculate the angular acceleration, right? So what we're going to do is look at the free body diagrams of each of these individual objects. So I've called the one on the left object 1, right? So I'm going to draw out the free body diagram. I'm going to call that rope here T1 as the tension of the rope 1. One thing to note, these are two different ropes, right? If you recall, like what we're talking about with pulleys, if you have a pulley and there's like this rope that coils around like that, and then a rope that coils that is attached from the middle onwards, those are two different ropes. So the tension in both of those can be different, right? But like in that case, these are both the same rope, right, for that pulley. Similarly, these are two different ropes, so T1 is not T2, right? So we're going to calculate some of the forces. I'm going to calculate in the down direction. Right? Because it's going to be moving, potentially. Mass 1 has tangential acceleration 1, tangential to the motion, right? Right? So mass was 12, right? Yep. Basically, you have to realize that that acceleration there, that's equivalent to our tangential 1, and that's equal to alpha r, right? And r, for this part of the grove is 0.2 in terms of meters, right? So it's, yeah. So when we simplify, looks like this, because 2.4 is 12 times 0.2. Right, so now we've got an expression in terms of alpha, and what we'll do is we'll rearrange T1 to be in terms of alpha. I'm going to call that equation 1. We'll come back to it. But yeah, we have two unknowns in that expression, right? Let's draw the other free body diagram. So we're going to call that rope going up, or going away from the body because of intention, T2. This one is 7 kilos. That's mg. This one, okay. Let's look at let's look at this, right? So 12 is significantly heavier than 7, right? But like, wait, that's a good way to put it. Okay, so if we take the sum of the moments, right? We don't know which direction it's going, right? But if you think about it, like, if we just assume counterclockwise first, right? It would be like T1, which is this rope, right? It's T2. This one's that, and then minus this one, which is 0.3, right? Minus our frictional moment. That's what we're going to come back to later. I've just drawn it out quickly up the top here because I want to explain. Yeah, basically the whole thing is going to be going counterclockwise, and if you assume wrong, that it's not going counterclockwise, it's actually fine because you'll get that a negative number, and then you realize that it's actually counterclockwise. Yeah, so if you took it as the sum of the forces, yeah, anyway, yeah. Point is, the reason I took this one as down for object 1 is because we're assuming that this whole composite disk is going to be spinning counterclockwise, right? And so this portion is going to go down, right? And this one's going to go up now, right? So it's going to be accelerating this way. Like that. And T2, sorry, it's going to be T2 minus the weight force. That's going to be equal to 7 because this one was 7, right? AT2, similarly, this is tangential, right? So that's just going to be 0.3 because the radius is 0.3 meters times alpha. When we rearrange for T2, we get this. Right, so here's the expression. And that's our second equation, pretty much, right? Now we want to look at the net moment on the system, so that's what I was talking about a bit earlier. So that's the net moment on the system. So we're going to be taking the sum of the moments, taking counterclockwise as our assumed direction of angular acceleration. So that it's going to be T1 multiplied by its lever arm minus T2, which is going clockwise, supposedly, multiplied by its lever arm, minus 2. So that's 2 comes from what we're given in the question, the frictional moment. Similarly to rolling resistance, that just is in the direction opposing the motion, right? Okay, and then they gave us IO. We're going to plug in our equations, right? So this one was this. This one was 2.1. Right? Yeah, there's a bunch of maths involved here. So that's that multiplied by 0.2, right? That's that multiplied by 0.2. We have negative 2.1 alpha multiplied by 0.3, which gives that. We have negative 68.67 multiplied by 0.3, which gives this, minus our frictional moment. That's the same right-hand side. So as you can imagine, we just grouped the alphas. And then solve for alpha. That's in radians per second squared. Right? Yep, we assumed everything was right. We didn't get a negative number, so our angular acceleration is going counterclockwise, right? Oh, that was a question. Okay, cool. I was just asking for that pretty much, right? Yep. Do you guys have questions in person? Let's tab back out. Oh, you got a question? Yeah.
Oh, so the 2 Newton meters, that was to stop friction on the system?
Yeah. So let me just quickly draw out. So like, do you remember the question that was like, there was a car and it was being towed by some truck or something like that, right? And it said it gave us the rolling resistance as like 200 newtons. I can't remember, right? That was equivalent to Fk, which is the kinetic friction, right? Which we know is constant, right? So it's always applied as long as it's above a certain like acceleration, right? It's going to be applying this, and you know that is equal to that times that, right? It's very similar, but they gave us the rolling moment instead. So instead of needing to do all those calculations with coefficient of kinetic friction times whatever, they just give it to us. So we just subtract it off, and it goes in the opposite direction to the motion, right? Yeah, so we subtract it. Yeah, if that makes sense. Okay, I couldn't tell if my computer was lagging or not. Yeah, I don't think there's any more questions since I last checked. Okay, let's talk about work energy methods, right? So this looks familiar, right? From particles. And luckily the Holy Grail equation stays the same, but each of these individual ones will change a little bit. The elastic part won't change though. That looks the exact same. So yeah, just to recap, this is the work done from 1 to 2, state 1 to 2. This is your kinetic energy. This part is our gravitational potential energy component, and this is our spring potential. Energy, right? Yeah, the exact same as before. Let's talk about the individual parts. So this looks different. If you remember the particle version, this was like this, right? So we've changed F with the moment, and we've changed displacement with, this is what we call angular displacement. Right? That's this side. So angular displacement sounds scary, but it's basically just like this if you think about it. It just means what's the difference in angle, right? From the final state to the initial state, right? And you have to keep in mind that this is in radians. So you won't have to convert to radians if you don't have to, if we have no work, right? But if we have work involved in our question, like it's not 0, we have to keep this part in radians pretty much, right? Here's some common radian conversions that I've included. But yeah, so there's 3 cases, right? These are similar. If you remember before, for particles, it was by external forces such as pulling, or a frictional force, right? And now we've got an extra one, which is an external moment, right? So you'll see an example of this very shortly. But these are, yeah, I guess like let's talk about beams, right? Because I love talking about beams. So if you've got a beam, right, it's kind of the difference between having a point load that will cause a moment, right, on the beam, and having just a point moment, right? pretty much it. Like, yeah, it could be the same thing pretty much, right? Oh, actually, not really. Okay, yeah. Ignore what my most recent sentence. But basically, in these two cases, it adds energy to the system. And this one, it removes energy. Right? Let's look at our other components. So, just quickly talking about the bottom one. This is the same as particles, right? Because if you remember like what a particle situation looked like, right? So we have a slider, and then you have this spring, right? It goes here or whatever. The spring is still a linear object, right? It's still like a 1D rigid body with a length, right? And an example for particles, for rigid bodies that you'll see later might look like this. Right, so that's a rod, and then we have a spring attached to it, right? Like that or something, right? And so the spring is still a 1D object, and the only thing that's going to change about it is its length, right? So that component's the exact same. In terms of the first one here, kinetic energy. So if you remember kinetic energy for a particle, it looks like this. We've replaced m with our mass moment of inertia, and we've replaced our velocity with angular velocity, right? And this looks almost the same, but I've added an extra part. So let's draw out that situation again, right? So I've got that spring, whatever. So here's a rod, and this is at like 30 degrees or something. Yeah, so in state 1, the center of gravity might look like that, right? In state 2, say this is completely stretched out like that. That's a right angle, I don't know. And then a spring will look like this instead, right? That's G2. What we're saying is how much has this moved, right? So we can set any datum that we want, so that's the datum. That's H1. That's H2, right? So what we care about is how much has the center of gravity moved up or down, right? And if it's gone up, it increases in gravitational potential energy. If it's moved down, it decreases, right? Yeah. Does anyone have questions regarding that? You know. Yeah. What I might do is I'll give you a break first, and then I'll do the quizzes afterwards. Alright. So just a QR code. So slow today. I'm just going to paste it in the chat. Yeah, so regarding this question, basically I use a software called NoteWise, and I have a Samsung tablet. I think it's like $11 or something. You pay it once and then you have it forever. And I don't know, I found it really useful. In the long run, it costs less than paper. So and I feel like it's more useful than paper. I actually look back at my notes more compared to when I just did physical notes, so I prefer this. If you have an iPad or you're considering getting an iPad, a good app is, what's it called? Good Notes. It's called Good Notes. Yeah. If you're using like a Windows computer, I don't know if there's like a good equivalent. Like if you use like a Surface Pro, for example, and you flip it out like a tablet, I think the next best option is just OneNote for that one. But yeah. Use a Wacom for taking notes on OneNote. Nice. Yeah. I don't think OneNote's bad. I think it's quite good, and I know like other demonstrators who use OneNote. It's quite good. Um, I think for me, I had a I have a, what's it called, Surface laptop, and you can't bend the screen back the whole way, so it's really awkward to draw on it. So I ended up getting a Samsung tablet. Um, yeah, Wacom. That, from what I know, that's like a drawing tablet. If you have a drawing tablet, then it's gonna draw well. So you can use whatever software, and yeah. Yeah, stone slab, sharp rock, to the old school way. But yeah, I don't know. I decided to get a Samsung tablet over an iPad because I already have a Samsung phone, so everything was just more compatible. Yeah, that's how it worked out for me. Yeah. I'll have to check if I'm running the revision workshop. Hopefully not, because I'm quite busy next week. So yeah, I'll just have to check. But I'm pretty sure it'll be during the lecture time. Yeah, I might give you like 1 more minute or so for the break. Oh yeah, you got a question.
Sorry, what was the date and time of the final again? Is it on the second?
Let me get that up.
Oh, it's on Saturday.
Yeah, I think it's a Saturday. Is that one there?
Is this would it be in person or online or do we have to
Online.
choose?
It should be online.
I just wondered if that like
It's 100 minutes long, and it'll be online like the midterm.
mostly just like just maybe getting notes. Like I feel like when I write down sometimes it's what I write down and like notes that posted like teachers they just see more like easier for some reason. I don't know why.
Yeah, like for me, I do all my exams that are online with paper still, and I actually practice with paper because even though my notes are neater on this program, I still write slower than pen and paper actually. So if you want to go quick, I think pen and paper's better for like exam situations, and it's also good to practice with pen and paper. When you're doing like your practice exams or whatever, because then you get used to writing on like physical paper again. If you're like me, where you have like when you're using digital for a while. Yeah.
I'm curious how the font came about. I should have set the font came right price. We don't really have a book, but she set it up.
I mean, how all my COVID exams worked back then was at the time that the exam drops, there's like a PDF that's unhidden on Moodle, and then you look at it and it's got like the list of questions, very similar to like how you see a list of questions for the tutor questions or whatever, and then you can answer it on like your iPad and then export it as a PDF, or you can do it pen and paper and then take photos of it or scan it and then upload that as a PDF. But like what you write out, it doesn't necessarily need to include the question. Yeah, it just needs to include like the question name and then the response. It's like question 1 and whatever response and stuff. You probably don't have to print out whatever you get on Moodle because you'll have to spend time printing it out anyway, right? So they'll be slower. So yeah. Okay, let's get back to it. Let's do the quizzes. Just check. Shuffle questions off. Yeah. All right. Yeah. As usual, could you please join this once I display the QR code? Let's get charged my laptop. Yeah, I assume not too many more people are joining. Yeah, okay. Let's just run it. Oh, we got another one. Oh my god. I'm gonna turn off the music. Right. Okay, I'm gonna turn off the sound. Just be waiting until most people finish up. Very good. Maybe like 10 more seconds. Something. 3, 2, 1. Okay, sorry guys for the slower people. Just don't want everyone to be waiting. Congratulations to these individuals. Alright, let us review them. Oh boy. It's not looking good. Yeah, I mean, hopefully you feel like this shoot's not as bad as last shoot. I think when we get to the work energy stuff, it's gonna feel very familiar, and same with like the momentum stuff, assuming that you've practiced a bit for like the particle versions. Yeah, like the angular acceleration stuff, that's pretty new, but yeah, it's gonna get a bit easier throughout this shoot. Okay, so mass moment of inertia. Yeah, so there's a lot of little tricks here, but this one's the correct one, right? So 4 times the rod about the ends formula. Each is 1.2. 1.2 because it's 0.8 and 0.4. Basically, if I zoom in here, that 90 is, yeah, that's where the 0.8 comes from. It's just where this force is applied. So the whole rod itself is actually 1.2 meters. Why is this one wrong? This one is because, oh yeah, so you could use this formula if it said 2.4 meters, right? Because if it's spinning about the middle, it has to be the whole 2.4 meters, so 2 times the length of those rods that I said earlier. 4 times rods about the ends. Yeah, that one, the length is just wrong. So that was the trick with the 0.8. 2 times the rod about the middles. This one's wrong because you also need the weight of both the rods now as well, right? You need it to be 120 kilos if you're going to use that formula that is the rod about its middle, right? So yeah, that's the only one that's correct there. What's the most appropriate labeling for the pin support reaction? So this is one of the extra practice questions that I've given. Here's what I would do. Okay. Still kind of a, oh yeah, no, it's alright. So basically, this thing wants to move down and left, right? The center of gravity, the velocity is going down and left. And so the reaction in terms of the tangential reaction is going to want to resist that motion by going up and left, up and right, sorry. And the normal is going to want to bring the whole thing inwards, so centripetal, right? Yeah, for the first two, those directions just aren't the direction of motion, right? It's the direction of the acceleration due to gravity, but it's not the direction of the motion, right? Okay. This one is just a hard question. Actually, was it? Yeah, so the second and fourth one are just tricks. So those ones are not a part of what does work to a system or removes work from a system, right? So you had to tick both of those to get that one right. Yeah, anyway, so thanks for participating in that. Let's get back to it. Okay. So let's do question 2 here. We have, get my notes up. We have that we have this 10 kilogram rod, AB, and it's pinned at A and subject to a moment of 15 Newton meters. So in terms of like looking ahead, that M is going to slot into our work part of our equation, right? So that's an external moment. And we have these two states that it's describing, where one is when the angle is 30 degrees, that angle there, theta, and the second state is theta is 60, right? Another bit of important information is that the rod is released from rest. So that means in the first state, This is 0 radians per second, right? And the spring is unstretched at state 1 as well, so keep that in mind as well. So yeah, state 1 is when theta is 30. State 2 is when theta is 60, right? Okay, so it starts unstretched, right? I shouldn't draw that on here. So all I've done is I've redrawn the picture above. This is still general. This is still a general case, so it wasn't good to draw the L there. Okay, let's just. I like to draw a mini diagram of what's going on. Do like this. So this first state's when theta is 30, right? The center of gravity is here. This whole rod was 0.75, right? From there to there. So this was LO, right? So the unstretched length. Okay, first we're going to work out H1, and we can set the datum anywhere we want, as long as we keep the datum consistent for the second state as well, right? We'll call this H1. So H1 from geometry is 0.75 over 2, right? So it's over 2, because 0.75 is this whole length, but we only care about half the rod. Like this distance is 0.75 over 2, right? And then cosine 30. Cosine 30 because it's the adjacent side of this angle, right? So delta L1 stands for the, what do I call it? It's basically the difference in the length in the state 1 minus the unstretched length. But since it is the unstretched length, we have delta L1 is 0, right? So therefore, delta L1 is whatever that length is here in this picture, right? 0.75 sine 30. Looking at the geometry. Okay. So that's equal to 0. And we'll need this for the next part, right? Because if we draw out our second state, this angle has expanded to 60 degrees, right? G is here. Wait, I kind of drew this weirdly. Sorry, so this rod doesn't expand, right? This rod stays the same. What happens is our the springy component goes like that, I believe. Is that right? No, it is like, okay. What happens is it's like this. So it's still right angle. The reason is because we have this roller that keeps the spring horizontal. That's what the question says. The spring always remains horizontal because of the roller at C. So we're still gonna have these nice angles to work with, right? So that's LO, and that is delta L2. That total length is L2, right? 0.75. The rod stays the same length, but it's gone down a little bit, right? Assume that's the datum. The center of gravity's moved down a bit. H2. So this cos 60 instead, right? Which is lower. Right. So delta L2, so L2 minus LO, which was 0.75 sine 60. So that's L2. That's this whole length here, because 0.75, we want the whole rod, sine 60. That's that angle there, right? Minus our initial, our unstretched length, right? So I'm gonna delete my highlighting there because that's confusing. So what I've done is I've highlighted the parts which I'm going to use in my work energy equation later. We only needed LO for this step here. Yeah. So plugging this into the work equation. So what I like to do for slightly differently to how I've been doing it for particles is for the work energy equation, I like to pre-bake each part first before plugging it into the overall equation, because there's more steps for this one. There might be more steps basically, right? So I don't know, it's a change in style. So I'm writing out the formula. So IA, let's look at it. Let's look at this one, right? This is a rod, that's for sure. Is it a rod rotating about its middle or a rod rotating about its end? Correct, its end, right? So we want to plug it into this one. Okay, W1, omega 1 is going to be 0 because we're told that the system starts at rest, right? So it doesn't have any angular velocity. So therefore we're just left with this part. M of the rod was 10 kilograms. The length of the rod, 0.75, right? When we plug that all in, we get this. Right, it's not that bad. I'll do the spring one over here. Oh, you know what? I'll do them in the order which I wrote it out. So do the gravity one over here. Or G2. Okay. 10, 9.81. Hg2 we calculated earlier, right? Well, G because it's of the center of gravity, but it's 0.1875, right? And then of state 1, it's 0.3248. And this one, we don't have any unknowns, so actually we're going to be left with that amount of joules, right? Let's now do our spring. Same formula as particles. Every now and then in my working out, you might see x2. So x2 and x1 is just what I call delta L2 and delta L1. But I'll keep it as delta L2 in here. So the spring constant was 40 newtons per meter. These are all our pre-calced numbers from above. Right, this isn't bad. Okay, this part is kind of new. The work is the moment times the change in theta, right? Remember this was in radians. So we were given that. We were given 15 Newton meters, right? So pretty much we have angular acceleration is going to go that way. Oh, sorry, angular velocity is going to go that way, and the moments that we apply is going to go that way. So actually looking at everything clockwise, not counterclockwise, but it doesn't really matter. But we just have to keep that in mind, right? So here, I'm not doing negative 15, I'm just doing 15, right? So that's 15 Newton meters. In terms of change of angular displacement, just angular displacement, right? It's going to be, that's 30 degrees, right? Just turned into radians. That's 60 degrees minus 30 degrees, pretty much, right? That whole thing is going to be pi on 6 after we calc it. Anyway, it gives this number. So I've just rounded the pi out because, I don't know, just can't be bothered. Plug it into everything. So I'm just taking the numbers that we calculated earlier, right? Equals this. So when we solve for omega, well, we'll get this, and then we square root it, and then we get that this is in radians per second. So that's our final answer. So they just cared about what the angular velocity was, and we know that this whole system, we were analyzing it clockwise, right? So I guess this is good to keep in mind that we were talking about clockwise for everything, right? Yep. Any questions? No, all good. Check online. Don't we have to include this because the motion isn't purely rotational? Well, I mean, I think it is purely rotational, right? Because we're looking at a fixed axis rotation for this rigid body, not general plane motion, right? And therefore, we only have this rotational motion, right? There's no translation, right? Because everything, yeah. Anyway, yeah. Okay. Here I've decided to skip this question because it's very similar to the working out for the previous question, right? And that's a good thing. You're gonna run into a lot of questions that are very, very similar, but they're gonna change like one or two things in terms of like the work energy questions. But since like the rest is very similar, you're gonna be able to spot what's off about it probably, and it's relatively simple to do, right? There's not like a million different combinations of things I can throw at you for this topic. Okay. So, I believe the question that was asked online here. Here's an example of general plane motion, right? Hold on. Oops. Yeah, like here's an example of general plane motion, but you'll notice that yeah, like even though it's general plane motion, the work energy equation should still work out, and I'll show you why. Right. So, okay, here I've drawn out the question again. And like before, I'm going to draw a mini version of what both of these states look like, right? We have our spring, right? And this is in the unstretched phase or state or whatever. Here's our center of gravity. This rod's 0.6, right? And here we have the height of the center of gravity. We'll just call it 0, right? So this will be our datum, pretty much, right? And here we have our unstretched spring length, right? And we know that it starts unstretched. That's all good. Okay, let's draw our next one. So it looks something like this, right? But this is 30 degrees. This is still 0.6. Here's our center of gravity. So what's happened is our center of gravity has moved down. Let's call it 2G, right? And in terms of our spring distances, we can call this L2, and this can be delta L2, right? So this was our original length here. So we can calculate this just based on geometry, actually, right? So delta L2 is 0.6. That's the hypotenuse. Sine 30 degrees, right? So the far side of the triangle, the right angle triangle, is equal to 0.3 meters. And we know H1G is 0 meters. But H2G, right? So we want to take half of the length of the rod, because we only care about this part, right, of the diagonal, right? We care about this part of the diagonal, and then we care about the vertical component of it, right? So that's going to be sine. However, because the height's going down, right, it's below our datum, we have to add a minus at the front, right? Negative 0.15 meters. So yeah, those are our numbers that we're going to plug in to our equation. Okay. Okay. Okay, so here's how it's going to work, right? So we're in general plane motion, right? And so maybe I should have included this in my explanatory notes, right? Okay, so basically here's all of the kinetic energy happening in the final state, right? And it starts at rest, correct? So we're going to expand out this component of kinetic energy into the translational part and the rotational part, right? So again, we're in general plane motion. So here's where we account for it. So we're only talking about state 2, the final state, right? But we've expanded it out. I'm going to label that. So that is the translation. so rotation, right? But we can still plug in. So the mass is 15. Okay, so v, right? Linear velocity is equal to angular velocity times r, right? R is the rotational radius. No, I'll do it over here. So that, oh, actually, wait. Before I do that, I'll pose a question, right? Okay. So, is this a rod spinning about its end or its middle? I'll go up to the picture. It's spinning about its middle, okay? Because as it's moving, it starts over here, right? And then it goes here, then like here, right? So spinning about its middle pretty much, right? Once we account for translation as well. Okay. So we're using the about the middle formula. And we're solving for W2, right? That's W2 there. The rod is 0.6 meters long, so the rotational radius will be 0.3. So we're going to group the terms and we get 0.9, right? Like that. And then VE and VG, these ones aren't that bad. I'll do these relatively quickly because I'm conscious of the time. Because I still want to talk about momentum if I have time. So this is just the pre-baked numbers that I had from earlier. Right? Right. Okay, so the work is the moment times the angular displacement. So if we look at this system, do we have any work happening? The answer is no. There's no external forces or moments being applied, and there's no friction that we're considering either, right? So it's equal to 0. Right. We rearrange and get that omega 2 3.09 radians per second. Okay. Cool. Sorry, I actually forgot about this part being in the course. So I'm going to add that back into the notes before I upload it tonight in the what's going on? Yeah, I'll add it to this section here. Okay, I'm going to quickly check online for questions. What about momentum and impulse? Can't tell if I'm lagging, so like I like linger in the chat for an extra second. Do you guys have questions? It's okay. Yeah, go for it.
Why did this problem include translational kinetic energy instead of like, and the last problem didn't?
Wait, sorry, could you repeat that again?
Why does this problem like contain translational kinetic energy and the last one didn't?
Okay. Sorry, I did rush over that a little bit. Okay, so the question was, why does this question contain translational kinetic energy and the last one doesn't, right? So it goes back to, I'm going to go to workshop 9. Goes back to understanding of rigid bodies. So there's 3 types of plane motion, right? There's translation, which is like what you do for particles, as well as rigid bodies sometimes, but that's when you can treat a rigid body like a particle, is when it's only undergoing translation. So there's no spin or anything happening on it, right? The next is the rotation about a fixed axis. So in terms of that first question, it looks something like this. So that's our rod, right? And that's our spring, right? But it's happening about a fixed axis because this is happening about the pinned support, right? So here's another example of rotation about a fixed axis, right? It's basically when there's a pin support. That pin support's not moving, right? So we know that part's not moving, so the rest is just rotating about it. General plane motion is what we just saw, and it's where you have a combination of translation and rotation. So let's go back to the other question. Let's think about it moving over time, right? So it's going to start here at A and then B, right? This slot isn't drawn very well. Let's pretend it goes a bit further, because that length 0.6 is going to stay the same. As it's moving, right, like this, to this point, the center of gravity G is going to look like that, right? Not only is that rotating, but that's moving as well, right? So yeah, I don't know. That's my best try to explain. Add an explanation. Yeah. The path G that G follows. When we're considering this angle theta, that theta is going to change, right? There's going to be angular displacement, but it's not going to displace along a nice path like that. It's going to rotate and move in terms of translation, right?
I think I was under the assumption that B was stationary, so it was going to do like that.
Oh, no. Yeah, it's just because of how the question's set up. It's a bit of a weird question. I think it's the only question I've seen that's like this, to be honest. So that's when I was like a bit shocked. Because like I did these questions like a month ago, and then I just copied and pasted the answers over when I saw the question again. I've actually forgot about the translational portion. Yeah, so anyway.
Is it safe to assume if there's no like 2 fixed points, so both of them are sort of freely able to move like a spring or a roller, is it safe to assume that it's mapped up to measures like IG rather than like IO? Rather than like, not the end as a.
So okay, I know what you mean. So you have something like that, right? And it moves like that. What type of motion is this? It's translational, right? So that's something where you don't have to consider, or even this, for example, right? That's only translational because it can't rotate because this is in a tube or something that makes it not be able to spin, pretty much, right? So that's pretty much what you saw in particle, like work energy questions, right? It's like the slider going up and down this tube, right? And yeah, you're right. Like that was a good observation. Like the pin support kind of is always fixed there, right? So if there's a pin support, there's a good question. There's a good chance you only have to consider the rotational motion, right? But yeah, you're right. If you do have the specific case where you've got the rollers on both ends, and then it moves in like this weird way, that's general plane motion. Then you have to consider both, yeah, kinetic energy for translation and kinetic energy for rotation as well. I'm not going to get around to doing this last question, that seems, but I will explain the theory for momentum, right? So pretty much, angular momentum's denoted by h, right? So you remember E used to be denoted by g for linear momentum, right? And that one was mv, right? Momentum by itself doesn't really allow us to, solve any problems. But what's important is impulse. Impulse is the change of momentum, right? And that's where we can start using this information to solve questions. So the integral version of this formula is like this. And this is the version I think I've included in the questions, but it's basically just saying that, right? So if it says that a particle, if it says that like something happens over 4 seconds, right? You literally just plug in that for delta t. Yeah. It looks a lot scarier than it actually is. Not that bad. You do the same thing to find rotational resistance, right? And that's delta W. Okay, so for impulse, you also have to consider the translation, right? Especially yes, just you have to consider the angular impulse and the impulse in either of these directions sometimes, right? Like in the following question I'll show you. Yeah. And this is the same formula that you saw, I think on Monday, when we talked about momentum and impulse. This is the same one as the linear one, right? Here I've just decided to call it sum of the x forces in the right direction as taking as positive. And this is specifically just the x velocity. And it's of g, right? I'll show you what I mean, right? Let's analyze this question. This is a really cooked question, right? The ones that I provided are a lot simpler. So if you're doing your revision, start with the extra practice questions and then go to this one, right? And I'm gonna upload my solutions for it, but I'm not gonna have time to like do this one thoroughly, right? Let's read through it. So it says 40 kilo roll of paper. I don't know why it says paper, but let's say it's a 40 kilo disc, right? It has a kinetic friction acting on the wall here of 0.2. There's this vertical force P that goes up and causes it to spin, right? It's like, yeah. So determine the angular velocity of the roll when t is equal to 6, starting from rest. So that you already know your two states. Your first state is going to be time is equal to 0, and it starts from rest. And then your second state is going to be time is equal to 6 seconds, right? And that's when you have to determine your angular velocity for. Starting from rest. Okay. Yeah, this question, it really tests everything, because this is something that I haven't talked about in this lesson, but at the end of last lesson I briefly mentioned it. This is the radius of gyration, right? And if you want more of an explanation on the radius of gyration, look at the end of workshop 9. But effectively it's got this formula. right? And so when you're given K, you should be able to work out I very quickly, right? Because this is for all of the masses, like in that shape, and this is for, yeah, anyway, yeah, you should be able to find I very quickly, right? And this is going to be about 0.0 for this question. Sorry, I'm going to have to just go to my notes for workshop 10. Look through this working. Here's how it goes, right? So keep in mind, this is a very hard question, all right? The other ones aren't this hard. First thing you do is you find the mass moment of inertia from K, as I said. Next thing you do is you find the kinetic friction force, right? So that's just a matter of, well, actually, you don't know what N is, right? Which implies that you're going to need your sum of the forces, right? That's what we do here. We have a free body diagram, right? So the normal force is always acting away from the surface, right? And then Fk is going to be in relation to N. So FOB here is what I've labeled it. This member is in tension, okay? So between O and B, this is in tension. And that's what this arrow denotes. It denotes the tension force between those two. It's the exact same thing if this was a rope, right? But they've drawn it as a rod, but it's just in tension. This rod's in tension pretty much, right? Yeah, so you have your, okay. One thing to note is the center of gravity of this object as it spins around is not going to move, okay? The linear velocity of it is going to be 0, and that's what I mean by here. This is the velocity of g. So when I first did this question, I thought it meant the velocity here or whatever. No, it's the velocity of the center of gravity, which is not going to move, right? And then yeah, you plug in 6 for delta t, and then you take the sum of the forces. So that's in the positive direction, we have got N, and then this portion of tension acting horizontally. And then we have this expression. I'm actually, oh yeah, sure. Okay, so yeah, anyway, so we have this simultaneous equation because we're going to need to plug that in for y. We've got multiple unknowns, right? And then you can find the tension force and the normal force. Yeah, that's pretty much it. And then, so angular impulse, right? That's the formula from before. And we're solving for W2, omega 2, right? So since we know all this stuff now on the left, and we know I, we just solve for W2. And that's it. Okay. Cool. So that brings us to the end. Do you guys have questions?
So the radius of gyration is like a shortcut through all the geometry if it's given.
Yes. I'm going to give a very quick explanation of it again. So we got to...
Yeah, remember, there was a formula.
So sometimes they ask you to calculate the radius of gyration. So you go from I, and then m is the mass of the composite object, or like every object, right? And then you can get it. In this question, they gave you this, and you can work backwards to get this very quickly, right? In terms of physically what it looks like, right? In this question, the radius of gyration was 2.12, I can't remember what it was, but it's a bit over 2, right? It's like a radius, right? It's a measure of spread of how far the masses are from compared to its rotational resistance. Yeah, I don't know. It's the best I could come up with. It's a pretty hard, like, I've tried looking it up to explain it better, like, quite a few times, and I can't get the perfect explanation for it. Here I've just written it's a measure of spread of how distributed the mass is from the point of rotation. Yeah. Do you guys have more questions? Okay. I mean, like, after the class is over, just if you still got questions after that, so happy to answer. Okay, it looks like there's no more questions online. Yeah, this is good. Good luck for your exam, everyone. Yeah, in terms of what to practice, I don't really know, but I suspect that the finals will have a practice paper that they'll release, as normal for like most courses, right? Usually those are the best indication of what is going to be in your actual finals. So you want to practice those. That is like high value for your studies. Next, I'll look at probably the extra practice questions that are provided. They're on the same vein as the workshop questions because 95% of the workshop questions is taken out of the MEC booklet, right? Which is what I got my questions from. And then I've just grabbed more of those questions from the MEC booklet, and those are the extra questions. But I have like a kind of linear progression in the difficulty. Like you've seen the difficulty stars, like 1 out of 3, 2 out of 3, 3 out of 3, whatever. Start with the 1 out of 3 ones, then 2 out of 3, then 3 out of 3 if you have time, whatever. They cover most bases, I would say. Like there shouldn't be much that catches you off guard if you understand those, because to answer those you need a pretty good understanding of the like underlying concepts of the course. Yeah. No practice paper. Okay, well, hopefully you can just use what I've provided in terms of the extra practice questions. The best place to contact me is Teams. I think I check Teams more than my email. So yeah, you can just DM me or you can ask in the general forum and I'll try my best to get back. Yeah, in this next like week or two, I will be a bit more busy than I have been throughout the summer term here. So if my response is a bit slow, then yeah, sorry, but I'm gonna try my best to get back to everyone who asks questions. Yeah, but other than that, you're free to go, and good luck. All good, Jerry.